Hello, students. We are jumping ahead to 3.4. So we've covered addition and subtraction. We're moving into multiplication. Now, multiplication tends to be introduced. It can be briefly introduced at second grade level, typically comes in around the grade 3 based on the Common Core state standards. And students will develop an understanding of the meanings of multiplication and division of whole numbers through finding equal-sized groups, arrays, area models. So the idea is it's not just one thing. We don't learn multiplication by moving numbers in an abstract way. We want to understand the meaning of it. What does it really represent? Okay. Yeah, so I think those are kind of the big pieces there. We also get students should be able to interpret the products. Interpret 5 times 7 is the total number of objects in 5 groups of 7 objects each. And so the idea here with multiplication is that there are ways to model it. One model is repeated addition. It's the idea that I kind of repeatedly add the same number. It's not a great way to define multiplication that way for students who are going to continue on in math, because it's more of a scaling property is how we want to think about it at the higher levels. But for now, as you're introducing, it's not bad to kind of think of it. So what we're doing is we're scaling up. So we want to be 3 times as big. So we're going to scale up. And that turns out to match perfectly with repeated addition. So it matches, but it really doesn't encompass the entire component of what scaling up can be. And mostly the idea also is what do we do when we're multiplying by negative numbers? We're not repeatedly adding, but also how do we multiply by numbers that are not whole numbers? So we really want to look down the road for a definition of multiplication that would encompass all of these components. And we will kind of think about that as we go. But when we're modeling it, and this is different, a model is not necessarily the definition, but it's a way to represent it. And so repeated addition is a reasonable model. And we can take a look at the school page that's coming up as well. So in the school page, you'll see mathematical models. So you'll see groups, kind of rows and columns is pretty typical. Here's a group of fish, 8 goldfish in each bag, and you can kind of see there's 3 bags, so I understand it. Yeah, anyway, so we're talking about kind of grouping things, how many groups and how many are in each group. And those are 2 ideas that are very helpful when we also get to division. So how much is in a group and how many groups? Okay. Now, when we talk about definitions with multiplication, multiplication is actually pretty similar to addition. And what I mean by that is it still has that wonderful commutativity. And commutativity is the piece that says, hey, the 3 times 8 is going to be 24, and 8 times 3 is also going to be 24. So changing the order won't change the value. And that's why when we give a definition to the terms here, we call those factors. Both of them are considered a factor. If you do go back in time, there was a time in America, 1900s, and I do happen to have a math book from there that was passed down from my grandpa. But there was a time where we would name the first number and the second number with different words to kind of convey exactly which order we want to put a grid in. But that fell out of favor over time because, again, the commutative property indicates the value is the same. And so this is kind of the most common piece now. We call both of them factors, and the result over here is known as the product. Okay, and this is a tough thing, I think, for students, is the word factor is being used as a noun here, not as an action or a verb. When you were in, let's say, an algebra class, you might have taken something like x squared minus 4, and the teacher said to factor it. Factor now is being used as a verb, and you would turn it into 2 quantities that you would multiply together to get here. So this is kind of undoing the multiplication. So the idea of factoring a number, you want to think of it as undoing the multiplication, turning it into the individual values. We do the same thing over here when we factor a number like 24, because 24 could also be 6 times 4. So 6 and 4 are factors of 24. The process of taking 24 and turning it into those numbers is known as factoring. If we did that with addition, 24, for example, could be seen as 19 plus 5. We tend to call that idea partitioning. So we partition, we break it up into its parts. Partitioning. And this one up here is known as factoring. Okay, so you'll hear those words being tossed around from time to time in math circles and in math textbooks. All right, so there's the idea here. Let's see here. We have repeated addition model, the idea that I just keep continuing repeating the addition as I go. And if I do repeat 4 plus 4 plus 4 plus 4 5 times, the end result of 20 matches with this. Notice it also matches with two groups of 10. So 2 times 10 is also 20. And you can use these with what are known as Cuisenaire rods. So some schools will use those. I think we have them from time to time. I may use them later when we get to fractions, but for right now, I'm not going to bring them out. Okay. Here we go. Here's the definition of multiplication of whole numbers. Now, this is based on the repeated addition model. So for any whole numbers A and for a natural number N. Now, notice this wording is intentional. Whole number A, that could be 0, 1, 2, 3, 4, and so on, right? And a natural number N. So what that means is we could not have 0 because that 0 is not a natural number. So this encompasses multiplication of everything except 0 times 0. Okay, you could have 1 times 0, 1 times 2, all those are possible, but just not 0 times 0 because that is not what the definition says. Okay, so there we go. There, highlighted that a little bit with natural number. All right, other ways to model multiplication. Other ways to do it, instead of just adding the same thing repeatedly or drawing it on a number line, we could make an array model. Array models show what tends to be rows and columns. You see these with eggs, you see them with donuts. There's a lot of objects that do include these. You could make them on a grid where the dots are representing the value. You could make them with a grid where the boxes represent the value. So all of these are considered an area model or a box model, sometimes called a grid model. Okay. Another way of representing it is what we did with sets back in chapter 2, the Cartesian product. The idea of taking every option you have. So for example, you have to choose a type of bread, light or dark bread, and then you choose some of the condiment options. Let's say you get to pick one on this particular sandwich. So you get to choose your bread and you get to pick one condiment, and this is a certain price. So what you can do is you say, okay, take my order and break it up first by the type of bread. So I say dark or light. After that, I branch off all of the options. This is known as a tree diagram, and you can kind of see if you tip your head to the side, it looks like a kind of a big start of a tree. We've got the stalk, or even it could be a not a tree, just some kind of flowering plant, but you got the stem or the base, and then it branches off, and then those branch off again. And so when you look at it, you'll be able to count all the different possibilities, and counting all those different possibilities gives you the total of 2 options first and 3 options second. So this is a model of multiplication. If a student wants to see why is 2 times 3 equals 6? Well, if you had 2 options first and 3 options after that, you would have 6 total options, and you could actually show them all of these options. If you prefer, you could also write this into a table that matches. Notice the same thing. This turns it into the area model. And so if you need a definition that's based on the model, and this is what's interesting, is you can define things based on your model. So for finite sets, if the number of A is little a, the number in set B is little b, then A times B is equal to how many things are in that Cartesian product, A cross B. Okay. All right. So we've got a couple different ways to define things. Next, again, we have products and factors. They mention those, and they say, now let's talk about the properties. Are these closed under multiplication? Well, it depends on the set. If you want to be perfectly clear, it totally depends on the set. Some sets might be closed. Let's take a look here. Let's see here. The set containing the number 1, for example, would be closed because the only thing you have is 1 times 1, and 1 times 1 is 1, which is back in the set. So that's kind of a fun set that is closed under multiplication. So when we write it, we would say closed. Oops, let me spell that correctly. Closed, and then you'd have to say the operation. And the reason is if you tried to check the set containing 1 with addition, then 1 plus 1 would equal 2. 2 is not in here, so this is not closed under addition. Okay. It's also not closed under subtraction, right? Because 1 minus 1 is 0, and guess what? 0 is not in that set either. So a different set could be closed under different operations. This is the thought process that we want to go through. Okay, so closure of multiplication says if you take two whole numbers and you multiply them, you're going to get a unique whole number. Now we can do that for other sets. I did it with the set containing 1, but you could do it with like the set containing 1 and 2, let's say. So then, okay, let's see here. 1 times 2 is 2. That's in the set. 1 times 1 is 1. That's in the set. 2 times 2, ooh. 2 times 2 is 4. Ooh, 4 is not in the set. So you would say not closed. Okay. This operation, the multiplication, is commutative with whole numbers. It's associative, and there is an identity element. Many of you might know the identity for multiplication, which just means take any number you want. I'll take Michael Jordan's number, multiply it by some number, and get back to what you started with. What number has to go into this box? And the number turns out to be the number 1. So 1 is the multiplication identity. Okay, that also means over here that 1 times 23 would also work, and it does. Okay, so perfect. So this is what it means to have a multiplicative identity. Okay. Let's continue on. Ooh, let me clear those drawings out. Okay. So we have commutativity, associativity. They show some images if you prefer to have a visual as to understanding why commutative and associative properties work all the time for multiplication. They do. The commutative property says the order doesn't matter. If you're thinking about it as an array model or a area model, if you think about just twisting it, it covers the same amount of area. Whether your yard is 5 by 3 or whether it's 3 by 5, you have exactly the same amount of area. Associative property would be kind of stacking things on top to make a larger grid. If you stack them horizontally or vertically, guess what? It's the exact amount, exact same amount of area or volume in that case. Okay. Let's see here. Multiplication property of 0. Oh yeah, this is a fun one. We actually use this a lot in algebra. And so those of you who remember some algebra be like, oh yeah, I remember that. So let's talk about what does this mean? It says if you take a number, any number you want, and you multiply it by 0, guess what you get at the end? You get 0. And that's true on both sides. 0 times any number is also 0. So this is a property that we're going to use a lot. It's a fantastic property. I think you're going to appreciate it. Where did I say in algebra? What does this mean? Well, let's just say in algebra, if I multiplied two numbers and I got 0 back, then looking at the sides over here, you could conclude, well, either A is 0 or B is 0. And don't forget, the or means at least 1. So that's possible that both of them are 0. And that is perfectly okay. And again, this definition, this property of 0 for whole numbers says for every whole number. So it's okay in this case to have 0 times 0. The reason it wasn't okay in the other definition is if you're building a repeated multiplication and you're going to say, I'd like to do 9 plus 9 plus ... plus 9, and you want to do this 0 times, it isn't clear that you would get 0 from this because you have written nothing down. Okay. So we want to be clear in our definitions, and that's why we tweak those just a little bit from time to time. If you're ever confused on why did you word it this way, please let me know, because there is always a reason why. All right, next up is the distributive properties of multiplication over addition. We actually use those in the addition section, and that's because we've had them in prior classes. So let's take a look. So this one is an important piece. If you think about multiplication in that model of repeated addition, so if you had 3 times, I'll just put algebraic pieces x plus 2, that means 3 groups of, which means I could have x plus 2 plus x plus 2 plus x plus 2. That's what I have. So in this case, I have, so I have an x plus an x plus an x, that gives me 3 x's. I have a 2 plus a 2 plus a 2, which gives me 3 2's. And yes, I could simplify this to be 3x plus 6, but I want you to notice that the 3 was distributed to each of the terms. So we do have distributive property over addition and also over subtraction. And we'll see that addition and subtraction turn out to be, I guess addition is the key element there. The subtraction turns out to be convertible into addition as we go. So this is the distributive property. You can use it with numbers. Personally, I think it's a fantastic way to do mental math. So let me demonstrate that briefly. So what would it look like for mental math? Let me grab some white space real quick. Okay, mental math. Here we go. Click back here and get me some color. Okay, so mental math. Here's like if I'm doing a math multiplication problem, and maybe you've tried to do this before, but let's just say I'm doing 7 times 23. If I was doing this old school wise, I'd have to write down the 23, I'd write the 7 down, I'd be writing something down and regrouping, as you referred to it as carrying. Remember, we're calling it regrouping now. And I would struggle to try to keep everything in my head as I went. Instead, what you can do is rewrite this using the distributive property. And the reason is single digit multiplication is much easier. 7 times 20 would be 140. Well, I can keep 140 in my head because it's like 14 with a 0 at the end. And then 7 times 3 is 21. So then I can add these together, and adding these numbers together in terms of hundreds is easy. Tens, oh, that's not too bad. And then add your ones, and you can get the answer really quickly. So this idea of being able to do this skill, this distributive property, is huge. As a matter of fact, we're going to see the reason all of our algorithms work for multiplication is the distributive property, because that's really what you're doing for every one of the algorithms as we continue on. All right, so there's the distributive property listed out. Works for all whole numbers. It actually works for all numbers, which is fantastic. And they put in the subtraction one as well. Because they want this to be for whole number operations, and you can see that at the top of the screen, they make sure that they say B has to be greater than or equal to C. They do that so that you do not end up with a negative number. I want you to be clear, though, this distributive property works regardless of that. The reason they're adding it in now is depending on your age group, you may have to make that description. You may have to restrict the values for the age level that you're teaching. So they're including, here's a definition that works for your age level, perhaps. If you're teaching at a higher grade level, this restriction would be removed entirely, right? So just keep that in mind as you go forward. Here we go. So this is the area model once again shown. So if I have something over here like x plus y and on the top z plus w, you can break those lengths off and then think of multiplying the individual pieces. When you're done, you add all the components up. What you'll notice is this is the same thing as the distributive property in algebra. So what we're doing at this young level is trying to get students to begin to see these concepts in action. And that way, when they get to algebra, it does not feel foreign. What am I saying there? If you were thinking about this and saying, could you do this with numbers, Scott? And the answer would be something like, oops, I don't want to do 20. Let me do 23 times 41, let's say. Okay. Yes, you could build yourself a nice little model here where one side is 23. Let's call it this side over here. So this would be 20 and this would be 3. Okay, so there's worth 20 going vertically and then the little 3 at the bottom. And going the other way is 41. So I just have this little piece over here and this would be 40 and that would be 1. So then the region I'd shade right up in this spot would be 40 groups of 20. Okay, 40 times 20, which would be 800. But I'm going to write it as 40 times 20 for now. The next space over, this one here with the little top and bottom, this would be 20 times 1. The next one down here would be 3 times 40, and the last one would be 3 times 1. And I guess to be consistent, I probably should have written that first one as 20 times 40. I'll make that change. That's on me. 20 times 40, because we tend to go left to right. Okay, at least it matches the model. The value is, of course, exactly the same. All right, so what do I see here? I see all these groups. Now, when I write the product out, 20 times 40 is 800, 3 times 40 is 120, 20 times 1 is 20, and 3 times 1 is 3. So I could add all of these up and get 943. Visually, I get that value. Okay. Now, for a student, what they end up seeing is, oh, all I do is multiply each of these values, the 40 and the 1, each of these by every one of these. Each by every is a good way to think about the distributive property. Now, I know your teachers in the past might have given you something like FOIL. FOIL is good if you have binomial times a binomial. That's 2 terms times 2 terms. What I've seen in my own work is that students then would struggle using FOIL if I gave them 3 terms, which is not great. So because there is no FOIL for 3 terms, it would be oil, something along those lines, because you'd have to do each of the inner, and you have like an outer inner and an inner, and it just gets really complicated. So I'm not a big fan of using terms that are very, very specific. I understand you might have experience with it, so of course it's okay to use that because it is a way of a mnemonic device to help you remember do the first terms, then the outer, then the inner, and then the last. But just realize you might be better off learning something that would work in all cases. And each by every is going to work in all cases. So take each element of the first group and multiply it by every element or every term of the second. All right, so that's each by every. Let's continue on. We get another school book page showing the distributive property. Lets you see all the components, very similar to what I just showed. This is a grade 4. That was a grade 4 page. So grade 3, identify arithmetic patterns in addition and multiplication tables and explain them. So when you start looking at the patterns like we did in our number bases, we're going to do this in Fivania, of course. But in base 10, you'll notice the outer piece when you multiply, everything is 0. The next piece in is in a different color because that's just multiplying by 1. And anything multiplied by 1 is the identity. So you just get back what you started with. After that, you'll see a kind of a colorful region kind of going down. Those are the, in a sense, numbers times themselves. Those are perfect squares. And then you get a light shaded and a dark shaded region because the commutative property guarantees that those numbers across the line will be identical. 3 times 2 will be the same as 2 times 3. 7 times 4 is the same as 4 times 7. So those are going to be the same. So students don't have to memorize the entire table. The first two, the greens and the blues, are like almost given. After that, the diagonal, yes, you need to know your squares because those are unique. And then you need to know parts of these other components. All right. Let's see here. We do have properties of exponents. The idea of an exponent, base raised to a power. And again, we're dealing with whole numbers and n does not equal 0. So in this case, n is just a natural number. Then you can think of multiplication being like repeated in order to get this exponent. Okay. And what's great then is it ties together the foundational ideas of exponents. Because if you had 3 squared and you were multiplying that by 3 to the 5th, there might be an easier way to write that. But again, start by the definition. What does it mean to have 3 squared? Oh, that's 3 times 3. What does it mean to have 3 to the 5th? Well, that's 3 times 3 times 3 times 3 times 3, a total of 5 groups. But I'm multiplying between them. And so if you think about it, you're like, well, wait a minute, that's just a whole bunch of 3's put together. And the question then becomes, how many 3's? So 3, how many groups of them? 7. So I put 7 up here, and you might notice there is a really nice connection with those exponents. So 2 plus 5 does get me to 7. So this is a common misconception that sometimes students will multiply to get 10. But you can notice if you go back to the definition, there's not 10 of them that we would write out. All right. So again, this is one of our properties of exponents. It's listed here. If you multiply 2 numbers, they have the same base. You could rewrite it all the way out, or you could kind of shortcut it and say, hey, I could actually just add those exponents together. But if you do raise an exponent to a power, now we've got to think about it a little bit differently. So raising an exponent to a power. So if we had 3 squared, and then I raise it to the 4th power, this 4th power out here means take the 3 squared and do that 4 times. Okay, well now I have 3 squared times 3 squared times 3 squared times 3 squared, and I just had the property that if I multiply, which I am, with the same base, which I am, that's this property, theorem 3.9, then I add the exponents. So I get 2 plus 2 plus 2 plus 2 is what I really get. 2 plus 2 plus 2 plus 2, which is the same if I rewrite it using our repeated addition, would be 3 raised to the 2 times 4. In this case, I would have 8 3s. So it's important to realize which of these you're dealing with. And again, you're laying the foundation here. We'll be tending to use a lot of numbers in this class, but you're laying the foundation for algebra. So if you struggled with algebra, it might be also because as you were getting this foundation, maybe your teacher wasn't showing that connection between the idea and the process. All right, and yes, if you have two things, you can go both directions with theorem 311. If you have a times b raised to the n, you could kind of distribute the exponent over. Or if you have this 2 different bases but the same exponent, you could rewrite it that way. And so I do want to bring up something here with the order of operations. You have parentheses is kind of a key piece. Some of you remember PEMDAS. M and D are kind of together. Multiplication and division are read from left to right, whichever comes first. So it is not that you always do multiplication before division. And addition and subtraction are at the end with the same. Addition and subtraction are whichever comes first from left to right. So I've grouped them a little bit here for PEMDAS. And this is what I want you to think about is multiplication and division actually distribute across addition and subtraction. Okay, multiplication and division do not distribute across themselves. If you have 3 times 2 times 5, that is not 3 times 2 times 3 times 5. Some people think of I got to distribute because they think of the word distribute without the idea, the concept. Okay, this is not true. In fact, this first piece right here is basically the associative law. You can regroup it, but you cannot distribute it. Okay, so I'll put a little sad face here. Sad face teacher. Sad. Okay, now the reason I bring it up is theorem 3-11 illustrates that you actually can take exponents and distribute them across multiplication and division. You cannot distribute exponents across addition and subtraction. That's one more step down. So you can distribute kind of across one step down when it comes to exponents and multiplication and division. Okay, parentheses are a grouping term. They're not an operator. So it's not really, this is kind of where it ends. But this might be helpful for you if you've had questions in the past about why you can do it sometimes and cannot do it other times. Okay, and we get to this fun fact. Definition of a number to the 0 power. Number to the 0 power is 1, as long as that number is a natural number. We will expand that later to negatives and beyond, but for right now, it's a good starting point. And if you want to see kind of why that is, I guess I can do that very quickly here. So if you want to say, well, why is that case? Well, I think we'll probably see it a little bit more in section 3-5, but I'll give you a hint now. Let's say I had 3 squared, right, times 3 to some power, and I want to stay with exactly the same value I started with. Well, we know in order to stay with the same value, this quantity right here would have to be the number 1 because it's the multiplication identity. Okay. But we also know that in order with the same base, we would add exponents. So I know that 2 plus something has got to get me back to the number 2. And 2 plus something to get me to 2, this is the addition property and the addition identity. So that box would have to be 0. So what goes in the box? 0, which means 3 to the 0 has to be the number 1. So any natural number raised to the 0 power, you can think of the same argument and say, oh, it actually has to be 1. All right. Multiplication algorithms. Now we get into the algorithms. As you move forward, there is the base block approach, concrete model. We probably won't be doing this. I think we did show it. I showed it to you with the base model a little bit that we did in class. But we're going to do a little bit more. We have expanded algorithms. The expanded algorithms are written usually horizontally. You can write them vertically, and it matches up pretty nicely with what's known as partial products. Find the product of the ones, write it down. Find the product of the tens and ones, because it's be multiples of 10, put that down as well. The standard algorithm is written in the shortest form, and that's probably why it's standard, is it's just more concise. Okay, a couple pieces to remember. Anytime you multiply by 10, you move up in shape. So if you have two tens blocks or two rods and three ones, when you multiply by 10, you have 10 times as many of each of those. So shape-wise, you move up to the next shape for each of them. If you move up to the next shape, that's the next place value, and that is why 23 times 10 gets you 230. It looks like it's really quick, and that's because it is. It's meant to be very, very quick. Okay. You could also show it using the properties, which is very, very long and tedious. Something we probably don't want to do that frequently because 23 times 10 is just 230. If you want to understand the real reasons why mathematically, we've showed it to you in a concrete way. If you want to understand the abstract way, this is what you would do. And again, it's a little tedious. Okay. All right, let's talk about the other algorithms. Partial products algorithm. Partial products, you write down as you go all of the products. You can start from tens, you could start from ones, it doesn't matter, but you do all the partial products. You can see them visually as the partial products, but you can also write them down in more of an abstract way. So here's the one where you start with the tens group. So I have 10 times 20. 10 times 20, I did that. Then I have 10 times 3, got it. Then 4 times 20, and then 4 times 3. So again, what you're looking at here is if you had 23 and 14, you'd be saying, okay, I go here and there, and then here and there. If you want to be confused, I hope you're not, but this is your standard algorithm, just without the writing things above and regrouping. So in your standard algorithm, the traditional algorithm actually combines two steps into one. So instead of doing all of these smaller pieces, which for students who are learning this are probably easier because it's single digit multiplication. Instead of doing that, you start combining them. And so what you end up with is 23 times 14 in the traditional way, and you would multiply 4 times 23. So your first line would actually be 4 groups of 23, followed by 10 groups of 23. And then you're going to add those together to get 14 groups of 23 using the distributive property. So here you would write a 2 down traditionally, and you'd get something like this, 92. In this algorithm, you still get the 92. It's just separated into 80 and 12. Okay, the next one over, you'd get 10 groups of 3. So I'd have 3 and 2. So this would be my 23 times 10, which again is just 230. In the partial products, you would have 230 as separate pieces. Let's keep rolling. What else do we have here? Lattice multiplication. Again, lattices are pretty fun. There is still a regrouping that still has to occur from time to time because the lattices break it into individual place values, and then you multiply, but you do have to regroup along the way. So let's see here. They're going to do 14 and 23. Make a box, and what you're doing is making a grid for each number. Put your lattices in, which is that diagonal line, and then multiply each time. So 4 times 3 would be 12. And notice the product will be 2 digits. A single digit times a single digit will always be 2 digits. It will never be 3 digits. 4 times 2 would be 8. So I write a 0 and an 8. 3 times 1 would be 0 and a 3. And 2 times 1 would be 0 and a 2. And then just extend your lines out and add down the diagonals. So 2 goes here. 8 plus 1 plus 3. Well, that's 9 plus 3. That's 12. I can't write 12 in a single box. We typically write a 2 and then regroup a 1 to the next place value. Our place values are not vertical. They're slanted now, and that's okay. And 2 plus 1 here gets you the 3. Can you do this in other number bases? Absolutely, you can. We will be looking at concrete models when we come back to Fivania, and then we'll be looking at ways to kind of do it without using the concrete model. You can go for more of a partial products approach, you can do a traditional approach, and you can do the lattice approach. So there's nothing wrong with any of those approaches. I mentioned to you ways of kind of doing mental computation using the distributive property, right? And so try a couple of these using mental computation. Even if you say to yourself, I'm not good at math, tell yourself, I could get good at this. And if you can get good at it, it's going to be much easier to kind of look at numbers and at least have a ballpark of what you're going to end up with. Okay, so there we go. Yeah, there's a lot of different, I guess some people call them tricks. I don't really call them tricks, but if you had something like 64 times 50, you could really think of that as 64 times 100 divided by 2, right? So you just rewrite the 50 because multiplying by 100 is way easier, right? So end up here and you're at 6,400, and then you just divide by 2. Well, what's half of something? That's also pretty quick. And so I can get 3,200 from that pretty quickly. Okay. So it's the more familiar you are with numbers, the easier math is going to be. Okay. All right. There we go. So there's kind of the way you could do it. Yeah, I think I'll leave it at that. All right, clear all the drawings. Let's move down. Estimation, the same type of thing. You can use compatible numbers. You can use rounding sometimes if you're estimating, getting a good ballpark here. But basically estimation, just understand estimating is getting a close answer quickly. So approximately how much money was collected if you had 4,500 people roughly and tickets were sold for $9 each? I might round this number down and that number, I would say 10 times 4,500. It's probably around $4,500. Yeah. That's a quick way to do it, right? If I went lower than that, I could say, okay, about this would be 4,000. Go up and it'd be 5,000. Well, 4,000 times 9. So this is another way to kind of do it here. 4,000 times 9 is like 9 times 4. So that's 36,000, right? And if I called it 9 groups times 5,000 people, well, that's 45,000. And then I could say, okay, well, I know it's between these two, and 4,500 is pretty close to halfway between these two. So what's halfway between these two would be another way to kind of go about doing it. You'll notice there's a difference of about 9,000. So I'd estimate half of that would be about 4,500. So I would then be saying right around 40 grand. That's a quick way to do an estimate. All right, let's see. I think we're getting close to the end here for this component. And that's it. All right, so that takes care of kind of a brief introduction to all of these pieces, utilizing concrete models, understanding definitions and our properties, and then seeing a few algorithms along the way. You'll see a few other algorithms in the homework sections as you do it, and you'll be asked to do things in different bases, of course, because that's what we're going to do in our class. All right, that's it for now. Off you go.